Okay, so in the last video we discussed the logic and the mathematics behind how we're going to work out the rotation we need to apply to our twist control in order to match our IK finally to our FK. In this video, let's go ahead and implement that logic, implement that mathematics in terms of our script. So I'm going to jump over into Houdini. Let's bring up the type properties for our asset. And before we do anything else, we need access to our twist control. That means we need to add a new parameter to our asset. And that's going to be the twist control parameter. And this is going to be any object that's null, so a null object. And that's going to allow us to grab our twist control. So let's accept that and specify our twist control with that parameter. So I'm going to grab the twist control and accept, then bring back up our type properties. We can now go ahead and edit our script. The first thing I'd like to do in terms of editing our match IK to FK script is block in some more comments relating to our script. So the first thing, well, what we're trying to do now is calculate the twist angle required to match FK. So calculate twist angle required to match FK, and we need to do that after we've done the previous calculations of moving our end effector and setting up the stretchiness. That's so that we know now the only difference between those bone chains is that twist angle, and we need to make sure that that twist angle is being calculated based on bone chains that otherwise are matched. Otherwise we'd be finding out angles between bone chains that aren't even existing with the same twist axis, and obviously that's not going to give us the correct twist angle. So we're going to create a vector from the start of arm to the end of our arm to end of arm, and that's going to basically give us that twist axis. We can then calculate the foot of perpendicular, so foot of the perpendicular of the elbow onto this vector. That's going to give us the base point for some of our different vectors. Once we have that, so with the root foot of perpendicular, so let's go ahead and just call that foot of perpendicular to maintain what we've been calling it so far. So with the foot of perpendicular, we can find out the base IK vector. Again, that's the IK vector going from that foot of perpendicular to our elbow when we have it set over to having IK rotations on the arm and having a twist angle of 0. We can also find out the FK vector. So we can find out the FK vector. Once we have those two vectors, we can now work out the angle between them. And that is our twist angle. We just don't know which direction to apply it in. So we can go ahead and we can say, we don't know which direction to apply this angle. We can try both and see which gets us closer to a 0 angle with FK. So that means we can apply both and see which is going to give us a closer angle between our new vector for our IK and that FK vector. And that's going to allow us to see which has given us a closer matching to what we were after. So with that, we can now go back and actually implement this. Now, because a lot of this is mathematics, it's going to be very hard to demonstrate what this is doing in Houdini. So I'm actually going to script all of this out and then test it, whereas before, of course, we were doing a few lines at a time and testing them, but all of this is mathematics based. It's going to be very hard to see if it's working or not working until the very end. So the first thing we want to do is create that vector from the start of the arm to the end of the arm. So I'm going to grab our arm start position, and hey, to grab our arm start position, we need to reference our start bone. So that gives me a great opportunity to jump back up to the top here. And let's bring in a few more parameters. We want to grab in our start bone. We're going to need our end bone. That's going to give us our elbow position. We also want to eventually set values on our twist control, so we need that as well. So let's go ahead and say our start bone is equal to who.pwd.node who.pwd.evalPalm, and that's going to be our start bone parameter. We need the same for our end bone, so end bone is equal to who.pwd.node who.pwd.evalPalm end bone. And we also want to grab our twist control, who.pwd.node who.pwd.evalPalm twist control. Now, whilst I'm here at the top of the script, later on I'm going to be calling on some of the Python math module functionality. Because of that, I'm going to need to import that module. I want to do that at the top of the script. So whilst I'm here, I'm going to import the math module. This is a module that comes with Python. It's available as long as you have Python installed, which you would have installed if we're calling on functionality in this script anyway. So we're going to import the math module of Python, and that's going to allow us to call on some various maths functionality that's really going to help us out with the various calculations we're performing here. So jumping back down to where we're trying to create a vector from the start of an arm to the end of an arm, I want our arm start position to be the translations, if you will, of our start bone in world space. So that means we can grab our start bone, and we can grab its world transform, which is obviously going to return to us a transformation matrix. And I just simply want to extract the translations from that. So I'm going to extract the translates. That's going to give us a vector with 3 components, and that vector is going to contain an X, Y, and Z location of our start bone, which is obviously is going to be the start of our bone chain. So that's going to give us our arm start position. We want the arm end position, which is equal to our IK handle target. We know that's going to be at the end of our arm. And we want to grab its world transform and again extract its translates. So here we could grab the IK handle itself, or we could grab the IK handle target. Since we know we've just matched the IK handle to that IK handle target, we can simply grab the IK handle target in this particular instance. We can now create a vector, an arm direction vector. And we want that to go from the start of our arm down to the end of our arm. That means we need to take the arm end position and subtract from that the arm start position. We also want to make sure that this is a unit vector. If we jump back to the whiteboard, we can see that that vector going down the length of our arm, that is B. B needs to be a unit vector from our upper arm to our end effector. So let's jump back over into Houdini. We need to make sure that this is a unit vector. That means we need to normalize this vector. So I'm going to say arm direction unit vector is equal to arm direction vect dot normalized. That's going to normalize that vector. It's going to return to us a unit vector with the same direction, but now it has a length of 1. So now that we have that vector, we can calculate the foot of the perpendicular of the elbow onto this vector. Now this is going to be the same for both our IK and FK, as we've mentioned before. And the first thing we need to know is the position of our elbow. So our elbow position vector is equal to the end bone dot world transform. That's going to give us a transformation matrix for our end bone, and we want to extract the translates. We know that the origin of our end bone exists at the elbow. That means if we extract the translates from our end bone's world transform, that will give us the elbow position. So now that we've got our unit vector for the arm direction, we've got the elbow position as a vector, we've also got the arm start position. If we jump over to the whiteboard, we have A, the arm start position, we have B, that directed unit vector, and we have P. That means we have all of the components we now need to go ahead and calculate Q, the foot of the perpendicular. So I'm going to go ahead, and the first thing I want to do is calculate TQ. That was the parameter that we're trying to calculate. And if you recall, TQ is equal to P minus A, the result of that dotted with B. So I'm going to say that TQ is equal to that elbow position vector, that was P, minus A, our arm start position. The result of that I want to dot with, so I'm going to call dot, because this will return a vector, and I want to call a method from that vector that is going to be the dot method, passing in the arm direction unit vector. So that's going to work out for us TQ. That's going to calculate, if we jump back over to Photoshop, the parameter for our line equation. We now need to plug that parameter into the equation, giving us A plus TQ dot B. So let's jump back over. We can now work out the q vector itself. So I'm going to say that the scaled arm direction unit vector, so this is going to give us the first part of that equation, and that's going to be multiplying b, our unit vector, by that parameter. So it's going to be equal to who dot vector 3 arm direction unit vector. So that is going to be b index 0 times tq. That's the first component. We need this for all of our components. Unfortunately, we don't have any functionality built in for multiplying a scalar by a vector, so we're actually going to have to do this component by component. So what I'm doing, I'm creating a scaled version of our direction unit vector based on tq, and I want to go ahead and do this component by creating a new vector 3, and that does need to be a capital, and basically passing in the arm direction unit vector index by index and multiplying that by our tq parameter. So let's paste that once and once more, and let's actually make sure that we highlight that guy. Fantastic. Control C and paste that once more. And obviously we want to pass in index 2 in this case and index 1 here. So we're going to take index 0, multiply it by tq, that's our new index 0. Index 1, multiply it by tq, that's our new index 1. Index 2, multiply that by tq, that is our new index 2. So with that in place, that has calculated that scaled arm direction unit vector. We can now say that the root of the perpendicular is equal to the arm start position, that's A, plus that scaled arm direction unit vector. So what we've done there, we've taken A and we've added onto A that tq dot B. So we now have Q, we now have the foot of the perpendicular. With the foot of the perpendicular, we can now find out those various vectors. To find out the base IK vector, we need to set our bones over to IK, and we need to set our twist angle to 0. So we want to set our bones to IK, so that's equal to 1, and we want to set the twist angle to 0. So to set our bones over to IK, I'm going to say who.pwd.palm fk IK blend dot get reference palm dot set pending. I want to set that to a value of 1. Now we know here that indeed we are grabbing the old FK-IK value here. We did set it over to FK. We can now set that over to a value of 1, and at the end of our script, as long as we make sure that we set this back over to a value of whatever it was originally, that is going to restore that original value. So where we are restoring our original FK-IK value here, we now want to actually place that at the very end of our script. So we're going to set that over to a value of 1. That will give us IK. We also want to set our twist angle to 0. We know that's on our twist control. So we're going to set our twist angle to 0 by saying twist control dot parameter. What parameter? We want to set RZ. We want to get the referenced parameter, and I want to set that to a pending value of 0. So we're now setting that to a value of 0. With that, we now know that our elbow is in what I'd like to call the base location for IK. That means that the elbow to our newly found to the newly found root of perpendicular is going to be that base vector that we're going to find an angle to the FK vector. So now that we've got that in place, we can work out the elbow position, and from that we can now work out a base IK vector. So let's say elbow position vect is going to be equal to our end bone dot world transform dot extract translates, and with the newly found elbow position vector in that new location, since we set our IK to 1 and we've also set our twist to 0, with the new elbow position and that root of perpendicular, we can find out our base IK vector. So base IK vect is equal to elbow position vect minus the root of perpendicular. So that will give us a vector going from the root of perpendicular over to our elbow. So that's our base IK vector. We also need to find out the FK vector. So I'm going to say for our FK, we obviously want to set ourselves over to FK. So what we're going to do, we're going to set bones to FK, and that's equal to 0. Let's go ahead and put a space at the front of that comment to tidy things up. So who.pwd.palm fkik blend .get referenced palm .set pending, and now we want to set that back to a pending value of 0. And I want to grab the elbow position vector. It's going to actually be the exact same equation as before, so let's copy that. And instead of this being our base IK vector, this is now our FK vector equal to that new elbow position vector minus the root of the perpendicular, or the foot of the perpendicular. So I'm actually going to rename this to go with the naming convention we've used so far. There's actually 2 different names that you can use for that particular position. It's either the root of perpendicular or the foot of the perpendicular, and since I've been calling it the foot in all other instances, it makes more sense to call it the foot here. So I'm going to call it the foot of the perpendicular just to clean things up. So all 3 references to that have now been changed. So we've got the foot of our perpendicular, and now that we have that, we can find the angle between our base IK and our FK. This is going to be the twist angle. So to do that, let's go ahead and find out the angle, and we know that to find the angle we can basically take the dot product of those 2 vectors, but those 2 vectors need to be normalized to make life easier for us. We saw if we jump over to the whiteboard and bring up our layers, we can do a dot b, that will give us the length of a times the length of b times the cos of the angle between them. But if we make sure that they are unit vectors with a length of 1, then it's simply going to be cos of the angle between them. So I'm going to go ahead and say that we want to take our base IK vect, and I want to basically set that equal to base IK vect dot normalized. I also want to take our FK vect and set that equal to FK vect dot normalized. So that's going to normalize both of those vectors into unit vectors. We can now work out the twist angle between them. The first thing we need to do is call on the base IK vect and dot that, so call on the dot method with the FK vector. That will give us the cosine of the angle between them. We want to find out that angle as opposed to having a cosine of the angle. So I'm going to call on that math module that we imported earlier, math.acos. That will give us the arccos, or the inverse of the cosine function, which is going to allow us to basically take a cosine of an angle and extract an angle from that angle ranging between 0 and 180 degrees. But this is actually going to return to us in radians. So I want to take all of this and basically pass it in to a math.degrees method. So the math.degrees is going to allow us to pass in this result, which is a radians value, and convert that over to degrees, since our twist angle deals with degrees. So that's going to calculate the twist angle, but as we mentioned, we do not know which direction to apply that twist angle. So we can try both and we can see which will get us closer to a 0 angle with FK. So the first thing we want to do, set our bones back over to IK, then we can set a twist angle to the positive twist angle, and we can work out a new vector for that. We can then set over to a negative twist angle, get a new vector from that. We can then find the difference between each of those vectors and our original vector, our original FK vector, and that will allow us to see whether or not we are closer in one case or the other case. So I'm going to go ahead and first set our bones over to IK. So set bones to IK, that's equal to a value of 1. And to do that, I want to call on who.pwd .palm fkik blend .get referenced palm .set pending, and set that to a pending value of 1. So now we can go ahead and let's set our twist angle to a positive twist angle. So we're going to first try a positive version of this twist angle. From there we can then go ahead and set the twist angle to a negative twist angle, so we can try a negative version of that twist angle, and then after there we can compare the results. So let's do the positive first. So what I want to do is say twist control dot palm rotate Z, since that is the rotation that controls our twist, dot get referenced palm dot set pending twist angle. So that is a positive twist angle. I then want to find out our elbow position vect. That is equal to our end bone dot world transform dot extract translates. So that will give us the new position of our elbow. I then want to go ahead and say the positive IK vector. So this is going to be a vector going from the foot of our perpendicular to our elbow position when we set to a positive angle. I want to set that equal to our elbow position vect, subtract the foot of the perpendicular. So that is the foot of the perpendicular. And from there, I want to make sure that that is indeed normalized. So I'm going to say positive IK vect equals positive IK vect dot normalized. We can now repeat this for our negative. Instead, though, we're going to basically add the negative of rotate Z, or negative our twist angle into rotate Z as opposed to the positive. Now, before we do that, I'm going to actually calculate the difference so that when I copy this code and paste it, we also have the difference calculation in there. And the difference, in terms of the positive difference, is going to be an angle between that original FK vector, the one we're trying to match, and the new vector we've just created. So our positive difference is equal to math.degrees, since we know we're going to get an angle returned in radians, math.acos, which is going to take in a cosine, and we're going to call on positive IK vect dot FK vect. So we're doing the dot product of the positive IK vect and the FK vector. That's going to return to us an angle, which we can then pass over to acos. Acos is going to allow us to... Sorry, that's going to return a cosine of an angle, which acos is then going to return an angle, but that's in radians. And we want to convert that radian angle over to degrees. So now we can go ahead and copy all of these lines, Control C, paste them down here, and adapt them for our negative rotation. So in this case, we want to set the rotate Z to minus our twist angle. Our elbow position vector is the same. In this case, this is going to be our negative IK vector. And again, this is going to be our negative IK vector, negative dot normalize. So everything else is going to be the same, and obviously this now is a negative difference, and it's going to be equal to that negative IK vector dot producted with the FK vector. So we now have a positive and a negative difference. And we know that they're both positive values. They're both angles that are coming back. That means we know the difference, the angle between the negative vector that we just created and our target vector. We also know the angle between our positive vector and our target vector. Thus, if we take the positive and we see if it's less than negative, then if it's closer to the rotation that we're after, then that means that positive will be less than negative, and that means the positive was the correct rotation. However, if our negative difference was less than the positive difference, that means our negative rotation was the correct rotation. We basically see which is the smaller of these two values. Whichever is the smaller of these two values, that was the correct rotation. It's got us closer to that target. So what we can basically say is if positive difference is less than negative difference, that means that the positive was the correct rotation. That's the one that got us closer. That means we want to say twist control dot palm rotate Z dot get reference palm dot set pending, and set that to a positive of our twist angle. If that wasn't the case, we want a negative of the twist angle, but you'll recall that was the last thing that we set that to anyway, so we don't need to go ahead and set it again. We simply only set it to positive if indeed positive was the correct angle as opposed to negative. So with that, that should now match our IK to our FK, including the twist control. So I'm going to accept this. Hopefully we have no syntax errors. Indeed we don't. And let's set our FK up in an interesting setup where we know we need a twist angle involved. So I'm going to set up our FK. Let's rotate that around something like so. So we know we need a twist angle in order to match that. We can now come over and say match IK to FK. And there is an issue there. Arm start pos is not defined. So let's bring up our script, type properties. And that's on line 83. So let's hunt down line 83. And arm start pos on line 83. And that's because here where I originally defined it, I missed off the T. So if we accept that and try and match our IK to FK again, and indeed it looks as if all that went through. And now if we blend, we can see that marginally, apart from that very, very small rotation, again, that is caused by the fact that our bones were set up in the front viewport as opposed to the top, giving us bones that maybe don't sit exactly on the correct plane, etc. It's a very small rotation, something I'm not worried about. But you'll notice, look how close the twist is. That elbow position is in the exact correct location. We could jump back over to FK now and we could rotate this down. So we'd know that if that was a positive rotation, then something over here would need to be a negative twist rotation. So we could jump in and we could say again, okay, match the IK to the FK, blend, and we can see that indeed that is matching as well. So that's working out fantastically for us. So I'm going to go ahead and make sure all of these are zeroed back out. So let's zero out our FK controls and zero out our IK controls. And that is going to conclude the matching of our IK over to our FK, which is indeed going to conclude the setup of all of the controls on our arm. In the next video, I want to turn around and actually get our shoulder set up. So with that, that's going to conclude this video. Thanks a lot, everyone.